All right, Lab 10 tomorrow. A lot of things already provided, and today I'll provide you with more information on that code, so you can have more time to work on your project. Never wait until the last week. Okay, it's 20%. Can't change it back. Okay, you cannot change it back. Eventually, you cannot finish your project and you want me to change it back to like 30% for the final exam. You can't do that. So Reddit chose to do 20% for the project. It's a lot. So make sure you spend time on it. So for Lab 10, we are doing our the playback, okay, tomorrow. A lot of in-lab questions already answered in my on my website, so refer to that. And for Lab 14, what I'm trying to do is probably give you that in-lab questions through this in-class exercise. Could be on Friday or Monday, I'll see. Then on that Thursday next week, so you shouldn't just work on the in-lab, okay? So the in-lab should be done Friday or Monday, this or next week, okay? So you can take the time on Thursday to just do the soldering, so you can get it done on that day. Save your time to work on the projects. So assume that everyone can get it done, okay? So for Lab 15, so after next Thursday for track 2, you're pretty much already free, right? You have all the week to work on your project, including the week after, the Thursday after. For track 1, you'll use your soldered data board to work on one of the listed projects for Lab 15, right? And for presentations, we'll pick up 4 or 5 days, and I'll probably use a Tuesday for the last week to give you some time slots to do a presentation if we need to do so, okay? We probably don't have enough time to give everyone a 5 minutes presentation during these 4 days. Does that sound a good plan? Oh, okay. So I haven't fixed your board yet, but also other people requested for the PCB. Since I left a comment in Canvas saying you may have minor issues with your PCB design, because most of you have very common issues. For example, the trace width is too thin, which is going to introduce a lot of resistance, and the density is too low. You can make a 2 times less of a board footprint, but eventually it just becomes bigger. So what I'm going to do is today in the evening or in the afternoon, I will just pick up 2 designs from two groups and fix these 2 designs and record the process that how I fix it and post it to my website, so you can refer to that video to fix your board. Make sense? And also make a video about how to make the SD card footprint for layouts. Okay? Anything else do you need from me for projects or anything else for the labs? I already received several parts. I think the battery, DC motors, and a couple other sensors. Oh, the temperature sensor as well. It's in my office. So after today's class, if you want to grab the temperature sensors, directly meet with me in my office. I'll probably wait there for another 15 to 20 minutes for you to pick up your parts. Okay, I think I have temperature sensors, the DHT sensors, and the DC motors, and the 9-volt batteries, and also the MPU sensors as well. Okay, I mean the accelerometers. All right. Any other questions? Anything? No? So let's get into the Lab 10. Remember, I run a demo for you guys really quick. It's basically just using a double buffering technique to play the recorded data. It's basically just bytes from the SD card. So how that works? Let's get into the details today really quick. Definitely we'll cover the rest of the problems from the last in-class exercise after this, because we want to give the Lab 10 stuff a higher priority here, since it's going to happen tomorrow. But definitely we will revisit the remaining questions from the last in-class exercise, so you can turn it in today. Grab some in-class exercise over here. Okay. So when you are recording, there's a case R, okay, case R in there. It's okay if you haven't read the code yet, the in-lab code yet, but for recording, audio signal comes in, right? What's the first functional block is taking that signal. What's next?
It sends it to the ADC.
Mm-hmm. No filter, right?
Oh.
Filter and the mic are connected together, right? So it's just one functional block. Which filter did we use? Remember? I know this is confusing. Not really.
No.
So the Mac and the first order low pass filter are connected together. So what's the first order low pass filter doing here? So definitely it has a high pass filter to remove the DC offset, and then lift it by this DC off the desired DC offset over here. So it's lifting that to the middle voltage level of the whole range, which is 0 to 0.3 volts. That's why you are reading 128, because totally you are getting 256, right? It's 8 bits ADC. So anyway, so the first audio signal comes in to the Mac, and the Mac is connected to the first order low pass filter, and this pin doesn't have a header pin, so directly shorted, physically shorted to the RA5 pin of the microcontroller, which is connected to one of the ADC channels. Which channel? AN4, right? Keep in mind, when you are doing the ADC configuration, change it to AN4 in the ADC register. Otherwise, you are reading zeros. Sometimes you are reading 23s. They're just some floating charges accumulated on the pin. But it's just basically zero, nothing, okay? So what's after? I already told you, right? R means what? Read or record or recess. Record, right? Record. That's why I need ADC. Record, ADC, because the analog signal comes in, you need to digitize it. So you need ADC to digitize it. It's an analog signal. So a recording. So what's next? Speaker? You're recording, right? Recording, not play. So don't need a speaker. What you need for this?
Buffer.
Yeah, buffer. Yeah, but functional blocks on the schematic. Let's say. ADC converted to digital signal. So what are the digital signals? Bytes, right? Remember where these bytes are stored in? The AD, like this, right? Something like this. Maybe I spelled it wrong, but anyway, so it's a register directly connected to the circuit block inside the chip. So it's ADC's converted data already stored in this register. It's designed by the digital designers in microchip. So we're not changing, or not able to change it. So eventually you read from these ADCs, okay? And eventually read how many times before you write it into the SD card? 512 times, because every time it's writing and reading in the block, every block, and the block size is usually 512 bytes. So that's the workflow for the recording for the case R. If you press case R, this is what's happening. What about case? Which case? Case P, right? P is play. So we'll play. Where to start from? Where's the data?
The SD card.
Then where? So SD card comes from the SD card. These are bytes, right? So which module you want to send it out from the microcontroller? You want to send out bytes? Bytes are digital signals. These are like 8 bits. How do you convert 8 bits into an analog signal to the speaker? Because the speaker is only receiving analog signal, then play, right? It's an analog signal being played and getting to the audio amplifier and then speaker, right? So before that, right? Before that audio amplifier and speaker, and after the SD card, what's in the middle? What's connecting the two? PWM. That's why we learned these DDS from Monday, right? So how that works, remember? How do we use directed digital synthesis to convert a digital signal in 8 bits, right? In 8 bits to a analog signal. How that works? What's that? Low pass filter, yes, that's right. And PWM, so combined, right? Okay, let's see. Is that familiar to you? No? Since you didn't come on Monday? Let's run a paper for a question. So what is this doing? Check if you have attendance on Monday. Okay. So what is this? It's a passive low pass filter, right? It's a simplified version. And why we are not doing this in ENT Spice and Verify? This one. Why we are not using this one? Since I'm lazy, right? So low pass filter, it's just doing a low pass filtering function. So we can use this one, just show you how that works. Okay? Since I told you last time, if you have a low pass filter and you have a pretty fast oscillation, so the oscillation here is considered as pretty fast, okay? So you can see, even though it's not that fast, but compared to these RC circuits, it's fast. So this RC circuit has a pretty long, pretty big time constant. So your digital oscillation here is not able to fully charge and discharge the cap through this resistor because resistor is too big or too small. And why?
Too big.
Your question is too long, Professor. So the oscillation is too fast, and the time constant of the filter is too big, so your oscillation is not able to fully charge and discharge the cap. That's why you'll see it's oscillating. Okay, it's oscillating, or it's not fully in charge, fully charging that capacitor. You still remember how it's getting fully charged? What that looks like? Okay, so this is considered as fully charged, even though it's not good, but it's charging up to 5. So your output is reading a 3.3 volts, even though here is 5 volts. I just say 5 volts logic, okay? It's a 5 volts digital signal. So it's at least it's getting you 0 and 5 volts. So you are reading, if this is a digital output, you are getting 0 and 1s. So you're not losing your data, right? If your signal is too fast, or we just change the circuit, so make the signal is too fast to the circuit, it's not able to fully charge the top, and then it starts discharging, okay? That's why it's not able to maintain that oscillation, so keep accumulating charges in this manner. So eventually, can you expect what's really happening eventually? Because I'm only showing you 5 periods. Is this going to like eventually fully charging the whole 5 volts, or it will stay somewhere? What do you think? Let's see. We can change the simulation time, make it super long, adding 2 zeros. Okay, so we are just simulating for longer time. We'll see eventually what that looks like. Okay, run it. You know why? Because I don't want to show that input. Too many pulses. Delete. All right, so that's the output. Okay, it's not reaching 5 volts. It's not able to reach 5 volts. What's the conclusion do you draw from here? So for a certain PWM, Even though this is 50%, I couldn't see it, but I mean it's 50% PWM, for example, okay? Since I don't have enough points, number of points to plot it. But anyway, so for 50% PWM waveform, and I use a low pass filter to filter it, so the output eventually becomes what? Becomes what? Becomes an analog DC voltage. If I don't change the PWM duty cycle, I didn't change it. It's always 50%, even though the waveform looks pretty ugly because I didn't increase the number of points. Okay, it doesn't have enough number of points to plot it. But anyway, so it should be. Let me show you. Okay, let's look at the input again one more time. So that's the input. Okay, that's the input, and this is 50% duty cycle. And if you use the low pass filter to filter this 50% digital signal, and eventually you are getting a DC voltage, which is in between the two power rails, 0 and 3.3 volts. That's what you get. So input is a digital waveform with a certain duty cycle, and output will be a DC voltage in between that voltage range. So how do you form a sine wave though? You just have to keep changing that duty cycle over time in order to form different stars, okay? Form a sine wave. Let's take a look at it. It's lab, nope. Lecture something, see. Okay, this one. See? If this is 50%, you are getting a 1.7 volts DC, which is pretty much 50% of 3.3 volts. And then you increase the duty cycle, it's gonna lift. It's gonna lift that DC voltage here. Did you see this little ramp here? You see this little ramp? It's the same ramp. Don't scare you. It's the same ramp. Does that make sense? Okay, it's the same ramp. Okay, it doesn't take very long. Little ramp then stabilized at that DC voltage. So if you keep changing that PWM over time, eventually you are generating this kind of waveform very similar to a sine wave. So it could be a sine wave, could be whatever signal you have, depending on the bytes you have in the SD card. So you can basically, that's why when I'm reading from my SD card, I'm playing my song, my recording. Even though it's not a sine wave, something, because AC signal can be anything. They are just bytes. Okay? Just bytes. So just directly throw that bytes into the PWM function, writing function. You don't need any mathematical conversion or transfer function in there, which is really magical. I'll show you. Making things a lot easier. But does this make sense? The ramp and stabilizing and DC voltage. Okay, cool. All right, so for here, what's next though? SD card got the bytes, right? So the bytes are duty values for the PWM. So the next stage should be what? Okay, should be this, right? Or let's just use the PWM for now. And the next will be PWM is a module in your chip. Okay? So the function module in the chip. Then the chip has an output pin here, it's RC2, which is the CCCP1, right? So outputting that PWM waveform to where? To the low pass filter, right? To this guy. So you want to make a jump header. RC2. Did I say RC2 just now? That's why Dr. Carlson put RC2 here. Why? Because that's what? CCCP1. CCP1 actually. CCP1, which is PWM1 module. So you just put a little jumper here. So make the connections. The PWM will be directly sent to the low pass filter. And the pre is what? It's audio amplifier. If you want to connect a speaker to it, you need to use the low pass filter, the audio amplifier. So amplifying this analog signal. So put another jumper here, okay? And using the jumper here, because that's a schematic of the PCB, they are physically shorted already. They have the same name, even though they are not really have a trace here, but actually on the layout, they are physically shorted. That's how the Eagle PCB works, how the schematic works. You just give them the same name. So you convert to the layout, they will physically be shorted together. So these are already shorted together. Eventually the PWM will be injected into this guy and will output whatever your recording's analog signal should be to here, and being amplified by the audio amplifier. Then that goes to the speaker, so you can hear it. Okay, that's how that works. So what's next? Right? And what's next?
Audio amplifier.
Yeah, audio amplifier. And what? Speaker. Okay? Now, let's get into, before we do the number 2 question, we should go through the code here really quick. Try to provide it, okay? This is a template. Let's see. So when you are playing with that recording feature, what the first step should be? Record it, right? You have to record something in order to play it, right? So for recording, how that works, think about it. You don't have enough memory on the chip. You just have to do double buffering. Double buffering. The buffer is only storing 512 bytes for each buffer, right? So do the double buffering. Use a color as a flag. So how that works? Take a look at this and read it. Recording. This is recording, right? Recording. So record it first. The second paragraph is basically just repeating. You see here, and here's just repeating. Same stuff. So this is filling up the blue buffer. This is filling up the red buffer. Okay? So let's just ignore what the ISR is doing for now. Okay? So when the red buffer state is being filled, whenever that is being filled, what you want to do in here. See this semicolon? It's stuck. Okay? It's waiting. Whenever it's being filled, it's waiting. It's not doing anything here. It's not executing anything here in this case. Okay? So what's actually running behind the scene is the ISR. Because the ISR is going to interrupt no matter what. Okay? You don't have any like triggering or something. So it's going to interrupt. So whenever it's waiting in this while loop, it's going to interrupt. It's going to interrupt. So now, let's go to the interrupt. So for recording, it should be writing or reading. Writing. I mean, towards the SD card. It should be writing to the SD card, right? So this piece of the code. It's basically repeating. So now let's just look at this part. Okay. When color is red. Okay, when color is red, doing what? And also the state of the buffer has to be what? Right? If now the current color is red and now it's also being filled, do the analog conversion, put the analog converted data to the red buffer, right? Do you want to change the state before you reach 512? No, you have to fill. You have to put 512 bytes into the red buffer first before you can do something, right? The reason for that is you are writing and reading in 512 bytes, page by page. So I have to wait. So it's gonna constantly coming into this SR, depending on the timer. Okay, it's a sampling rate. You sample the data, comes in here. It's still waiting. So the P case or the R case is still waiting in the while loop. So it's constantly coming here at the sample frequency. So sample the data on the top.
What part of the code?
This is the Lab10.
It's in the ISR.
Oh, ISR.
ISR.
Yeah. It's pretty much at the bottom. See, this is the bottom already. So on the template you can see. All right. So keep filling this up until it reaches the block size, which is 512. Then change the state to filled, right? Change the state to filled. So if we draw the diagram, I probably will make this more clear here. So for the case R, okay, so for the case R, the case, okay, the case, not the ISR, for the case, it's trying to look at if this guy is being filled. If it's being filled. So during that time, during that while loop, it's a while loop, right? It enters the ISR. Enters the ISR. Okay, so in the ISR, it does a filling, right? So it's filling the red buffer. Keeps filling, just filling, right? Once it's filled, do what? Definitely change the state to filled, right? Because it's filled. Okay? Let's just keep it for now, okay? We'll change something here later. Once it's filled, do you still want to keep filling it in the ISR? No. So you want to do something, right? So being filled in the while loop, it will step out from the while loop just because of this. All right? It's gonna get out from the while loop. So let's come back to the R case. Okay. So it was here, but now it doesn't satisfy this anymore because it's not being filled anymore. The state has been changed to filled in ISR. So it's doing this write block, which is legit because you already have 512 bytes in the write buffer. So just start writing from this address to the SD card. Takes time to write. So while it's still writing, stay here because it takes time for the SPI communication, right? So after the writing is done, you got 512 bytes into the SD card. Then change the state to what?
Being filled.
Why?
Because it's done
Yeah.
sending the data, so you should.
So it's ready for the next run, right? Does that make sense for here? Because the state has been changed to filled in the ISR. And now you write it to the SD card, so it's done. So you can change it to being filled, it's ready for the next run. Okay? There's a really interesting thing to think about. I'm gonna ask you in a bit. So all this, so the address should be incremented. So next time it's gonna start from the next page. So the address should be incremented by what? By how much?
512.
Okay, 512 is block size, right? All right. So now let's keep drawing here. Being filled, whenever it's filled, you write to the SD card. That's what we just did, right? Write to SD card. And if you look at this read code, is there like certain control, like you can stay in the red or stay in the blue or no? Or it's just a sequence, certain sequence from top to bottom. This is definitely within the one while loop. If you don't press any key to interrupt it, it's gonna keep going back and forth. Okay? So now we are at here, right? So what's next?
The next while loop.
It's gonna do here, right? It's gonna do the blue buffer, gonna fill up the blue buffer. But the thing is, the color is not changing yet. So what you wanna do? Where do you change the color?
It's happened in the ISR.
Yeah. So you change the color when? You change the color while it's being filled, right? You change it to blue. So whenever it's running this while loop sequentially from top to bottom, it's getting in here and do the same job as a red buffer. So it's gonna be able to get into this because you already changed the color to blue, right?
Why do we use two buffers? Is it
Because one is
timing?
being recorded, one is being used to
Oh.
write into the SD card,
Okay.
right? Both takes time. So now we are here. So my question is, whenever it's in here, is that possible that whenever, because this interrupt is still interrupting in the same manner, right? With the same manner. It's not changing anything to the interrupt. Still the same sampling rate. So how do we guarantee that whenever it's running this piece of code, it's gonna do the blue buffer filling, but not the red buffer filling?
check what button? Valve,
Take a look. So it's gonna get into the ISR, do the writing, filling the buffer. How can I guarantee that it's gonna do this part, not this part? First is the color, right? The color is blue. And the blue buffer has to be being filled. It's an analogic, so have to satisfy both. So definitely it's gonna get into this one to do the blue buffer filling. Okay. All right. That's the reading part of it. What about writing? What does writing do? So reading, like what we said, right? So this is the diagram we drew here. This is reading, right? This is reading. And P case is writing. Oh, no, sorry. This is writing, recording, and writing, right? This is writing. Play is reading from the SD card. So with that you have to read from the SD card page by page. Okay, whenever you get a page in the buffer, you throw it directly to the. Oh no, actually, how do you do it? Good question to think about, right? Before getting to details, think about it. How do we do it? Reading and writing have to be both page by page for sure. And we know how to do it. It's not magical, right?
So you just take in a page and then parse through each of the bytes?
Yes. So you get a page, read into use the SD card reading, right? And then you can store it into the buffer. Then you can take every single byte from the buffer one by one and throw it to the PWM, because the PWM function, where is it? PWM function here. So now we're at reading, right? Reading. You're reading from the SD card and throw that bytes to the PWM module and play it, right? So we are here. We are here. So see, after you it's getting to here, you directly how that works.
The color is red. I think it's
Why do we have to put this in the ISR? You know, why you want to put this in the ISR? So this is the code that does the job, right? Play the song. Could you read it from the back? Remember in the beginning of the class we talked about that, right? How do you play a sound? Okay, you need to generate a analog voltage. How the analog voltage is being generated? Low pass filter. Okay, so low pass filter is from one pin. It's called RC2, which is the output of the PWM. Okay, so that's generating that certain duty cycle and being filtered to generate that analog voltage. Okay, so that's just one pin, right? Just one pin. It's RC2. So it's writing to RC2 with a certain duty cycle. Okay, so this, what is this? Red buffer index. What is it? Are you familiar with this? It's just the data, right? It's just data. That's the data in the buffer. So and you read that byte from the SD card. So which means it's ready. It's ready here for you to read. I'll let you know. I will let you take a look at it when we make it ready. But now for here, assuming that the buffer is ready, having that 512 bytes in there, so we're using the index to access every single byte. That's how you can write into the PWM, because you have to write byte by byte to that PWM module in order to generate a certain duty cycle waveform, and then being filtered, then generating analog signal, then that analog signal being amplified by the audio amplifier to the speaker, so you are hearing a song, right? That's how that works. Okay, so reading is reading from the SD card. No, reading from the buffer. So in that case, we need the data in the buffer first, right? Where do we make it ready in there? Where did we make it ready? It has to be somewhere else. It's not here. See, it's not really doing anything. It's basically just taking out byte and sending it to the PWM. That's it. These are not doing anything here, really. Changing the color, it's changing the state, right? Looking at the state, see if you want to change the state. It's not really doing anything. So 4 is playing forward, backward. It's not really doing anything, okay? See, this is just repeating. Same stuff. This is changing the color. Same thing, okay? So basically, it's just one line of code in the whole thing here, right? This is just one line of code. Just writing into the PWM, but nothing else. So when we got that ready into the buffer, where? It has to be in the P, right? In the P case. Okay, not too many cases. Don't get overwhelmed. R case, P case, ISR, that's it. Let's see P case. P case. So when you are playing with that lab, so first you need to press R, right? R to record it. Okay, so ISR will do the job for you. You are not basically manually doing anything else to put the data into the SD card. You do R, it'll be recorded. And then you do P, it'll be played. That's it. So let's see for P, what's happening here. Let's look into this part. So the address is it's using the old SD card address. I think it's 64 megabytes. But I think we should use a different value. I think it's 10. Should be 10 for us, because we are using 128 megabytes.
Isn't it rate shifting by 9, just dividing by
Dividing by 9, yes, yeah. So it's trying to change the address to the beginning. So move the address to the beginning, so it's able to start from the beginning. Because you have this much, right? And that's 2 to the...
To the 9th, 512. It's divided by 512 to tell you what you're losing.
Oh, 512. Okay, yeah, 512, not... Oh, yeah, that's right, 512, not this. Sorry, yeah. Yeah, 512, not this. Still within that page. What's that?
We change it to 9.
You move the address to the beginning of the page.
So
Divided by 9. Hmm?
So that 9 stays there?
9, yes, it's a 9. Yeah. All right. So that's the main part of it. Okay, that's the main part of it. What's happening here? If it's being emptied, oh, where is that empty coming from? Let's look at ISR. So this is reading, right? It's about reading here. Here. Because when you are writing to the SD card, it should be being filled. When the state is being filled, then you are writing to it. Okay? So when the state of the SD card is being emptied, you are reading from it. Does that make sense? Okay. So for reading, it should be, if you look at the color, it's a red, right? So this is red. What is this? Being emptied, right? Being emptied. So whenever it's done, whenever it's larger than the block size, you set a flag as empty or emptied. It's done. Okay, so these are the states. Now let's go back to P. Back to P. When you are reading from the block, refer to the reading function. First, you need this address, right? So see here, it's basically this guy. Okay. So whenever it's being emptied, staying here. Whenever it's done, move to here because you have 512 in the buffer, so directly write to it. Directly read from there, okay, to the buffer. So you get the data in the buffer, and then when it interrupts, it comes back to which one? In the reading?
In P.
In P? Yes.
Okay. So it's a lot like what was done prior in that line.
Mm-hmm. Yeah, not really too many new things. So whenever the buffer has 512 bytes, you can come here and take out one by one and read to the p.m. Yeah, so that's pretty straightforward, I think, for the lab. It's almost already provided to you guys. Play with it and move on with your project, right? Let me see anything else I want to talk about. Let's go back to the last one, okay? Number 5, right? In class exercise 4, okay? Number 4 is very clear. Let's just do a review on that really quick so you know what we are doing here. Number 4. Interpret that binary number as 4.4 format number. Like I said, right? So the register is storing a 0, 1. It's just a digital number, right? You just have to tell the computer that you are using the 4.4 format as a fixed point format. 4.4 format. There's no place to store a dot. You have to know that, right? It's just basically a register storing binary numbers. But you're telling the computer that anything is like four bytes here. The lower four bits will be the fractional number, and the higher 4 bits will be the integer. You just have to tell the computer this is how we format that number, okay? But the thing is, if you just look at the register, it's basically just these binary numbers. Just make sure you understand that first. What about number 5? 3.5 format for 3.6, which is a number. Okay, what's the number? How to do that? For this format, we know that there will be 5 bits after the point, right? Okay. So we can left shift this guy by 5 binary digits, which is equivalent to what? 3.6 left shift by 5 bits. I know, it's not a binary number. This is equivalent to what? Okay, let me show you. 125 is a decimal number, okay? Point is over here. I left shift the point by 1 digit. Is doing what?
Multiplying by 10.
Wait. Oh, left shift, which is actually this, right? Left shift the number, but right shift the digit, right? Okay. That makes sense? 125.0, okay? Left shift by 1 becomes 1250, right? Okay? So you do a left shift for decimal number, this is times 10, right? For binary number, you have 101.0, and you left shift by 1 digit is times 2. Make sense? So left shift by 5 is actually times 2 to the 5th power for binary numbers. Is that familiar with you? Familiar to you? Think about it. Decimal number, left shifted by 1 is times 10. Binary number, left shifted by 1 is times 2. Because this is a decimal point, this is a binary point. Okay? So, do this first. What is it? 3.6 times this gives you 115.2. And round it to 115. Okay? So what is 115? 0, 1, 1, 1, 0, 0, 1, 1. Okay? That's 115. And then what? Recover it. Recover it. So it's not changing the number, right? It's not changing the number. Let me know if this makes sense. This is already providing the in-class exercise, so this kind of simple math will definitely be on the final exam. Make sure you can do this in the future, okay? We'll give you more exercise later on Friday and Monday about this kind of problems. So this one shifted by 5 digits. Since you can definitely convert it to the binary format, but it's same thing. Decimal binary is the same number, right? So we're just shifting that same number to the left by 5 times, and we're getting the decimal format of that number. And then we round it, then we convert it back to the binary, then we right shift by 5 digits. This is recovering back to this point. Very, very close, not exactly, but very close. What's that?
Would the decimal point be 1 over to the left if you're shifting it over 5? Right, because we wanted in 3-5 notation, not 4-4. Because right now it looks like
The point was here, right?
Yeah. So go
Oh yeah. You mean three? It's a 3.5 format, right? Yeah. Thank you.
Yeah.
Yep. Cool. Good catch. All right. We'll see you Thursday and Friday. Okay.